So let me stress something about the mechanism of this reaction. So in this reaction, you have the alcohol that will react with the uh, POCl3, POCl3. And you can see the mechanism of this reaction in a McMurray in page 548. And you will form an intermediate of this sort. And so the alcohol will be attached to the OPOCl2. So there is one chlorine that goes away. And later on, the next part of the mechanism is an elimination E2 type that will require a relationship antiperiplanar between the OPOCl2 and the hydrogen atom that will be abstracted by the base. Who is the base? In this case, the base is pyridine. I'm giving you a structure there. That is the structure of pyridine. So pyridine will use the lone pair of electrons to abstract the proton that is antiperiplanar with respect to the OPOCl2 group. So this should be very reminiscent of what we learned in the second part of chapter 11. And you may recall that there we analyze that sometimes you cannot fulfill the Zaitsev's rule, and you need to contend in getting the alkene that is not necessarily the more highly substituted product. In that case, we were analyzing the product of the reaction of a dehydrohalogenation by a base, and we learned that the use of a strong base was preferred, and sometimes the product that you obtained was the alkene that was not necessarily the most highly substituted. So here, I'm giving you a couple of examples similar to that. So in the first example here, we have the OH that is trans with respect to the methyl group. See, it's trans with respect to the methyl. So in that direction, there is no hydrogen that will be antiperiplanar. The only hydrogen that is in that carbon atom is cis with respect to the OH. So that is not good. So that's why you don't have any other option than using the hydrogen atom that is on that other carbon atom, and that one is trans with respect to the OH, and that elimination will work because of the antiperiplanar requirement. So on there, you have formation of an alkene that is disubstituted. In this other example, we have the OH is trans to that hydrogen atom, and of course, it's also trans with respect to that hydrogen atom, right? So there you have the choice, right? So there you can choose in what direction you can eliminate. If I do it in the same direction as I did with the reaction above, in that case, I will get a disubstituted product. But if I eliminate with that hydrogen atom there, so there I will have the benefit, I will have the advantage that I will get a tri-substituted alkene. Tri-substituted. So, and of course, that is better because we know that tri-substituted alkenes are more stable than di-substituted. By how much? Sometimes it's not by a whole lot, but if you run the reaction under thermodynamic control, so there you will get formation of the more stable product. This next reaction we have here is the incorporation of alcohols into esters. So the general reaction is this. If you have an alcohol like this, ROH, reacting with the carboxylic acid, I will put R prime COOH. So then you have a reaction that is reversible, and you can form a product that will look like this. It will be RO. There you have the ester part, right? RCOO, ROCO, and then the R prime, right? What did you lose in this? What is the side product in this reaction? Water. So you have elimination of a water molecule. So this is a so-called Fischer esterification. And that is going to be the superstar reaction of chapter 21, where we get to see that that reaction works in the forward direction and in the backward direction. So you can perform the formation of esters, or you can perform the hydrolysis of esters to regenerate a carboxylic acid and alcohol. So for the time being, it will be enough that you know that when reacting a carboxylic acid, like this example here, benzoic acid, so that will be my R prime in the general reaction that I gave you down here. And so that will be the phenyl group will be my R prime. And in this case, the alcohol is methanol. So the CH3 correspond to the R group, right? So and what you form in this case is methyl benzoate. Another reaction that we will also explore in more detail next semester in chapter 21 is a little longer way to prepare the ester that involves first reaction of the carboxylic acid with thionyl chloride. Here you can see that thionyl chloride has several hats, right? Not only it works for the preparation of alkyl halides, but you can also form carboxylic acid chlorides. So reaction of the carboxylic acid with thionyl chloride, that will give you the corresponding acid chloride. And then this kind of intermediate is very, very reactive. So and then that one will react with the corresponding alcohol. You have two lone pairs of electrons, nucleophilic attack to the carbonyl group, formation of an O minus, regeneration of the carbonyl group, and then departure of the Cl. And in that way, you form your ester. This reaction is very high yielding, so it's much superior than the first method that I gave you, the so-called Fischer esterification. That method is not very high yielding. So if you have an alcohol or a carboxylic acid that is very precious, so it's not a very effective way to make the ester. Then we have the oxidation of alcohols. So the oxidation can be performed with a variety of oxidizing reagents. You can use KMnO4, CrO3, sodium dichromate, and this method all these reagents are rather strong oxidizing reagents. And as long as you have hydrogen atoms attached to the carbon atom that bears the OH, it will be possible to perform the oxidation. That means you can oxidize primary alcohols, secondary alcohols, but certainly you cannot perform an oxidation of a tertiary alcohol because that carbon atom doesn't have hydrogen, right? So and then there is another reagent that allows you to do similar thing, but the beauty of this reagent, this is called the Dess-Martin periodinate. The beauty of this is that allows you to stop at the level of the aldehyde. And so here you have the case of a primary alcohol, geraniol, that when you use this reagent, the Des-Martin periodinane, it will allow you to stop at the level of the aldehyde. In some way, this is an issue similar to the reductions of alkynes. You recall that in the reduction of the alkynes, if you were using hydrogen and palladium, you have to go non-stop all the way from the alkyne to the alkane. But if you were using hydrogen and Lindlar catalyst, in that case, you were able to stop at the level of the alkene. So similarly here, if you use KMNO4, CrO3, or sodium dichromate, there is no choice there. You have to go all the way from the primary alcohol to the carboxylic acid. There is no way to stop the reaction at the aldehyde level. But if you use Des-Martin periodinane, in that case, you can stop at the aldehyde. Very, very useful reaction. There is another reagent that performs a similar function that goes by the name of pyridinium chlorochromate, PCC. In the older days, McMurray was using PCC, but in the last few editions of the textbook, he changed to DMP, to the Des-Martin periodinane. I will tell you the reason why. The reason is that PCC is a chromium compound. Chromium compounds, chromium reagents, are not very environmentally friendly because chromium is rather toxic. So McMurray turned a little more environmentally friendly in his approach, and that is the reason he is now using DMP, the Des-Martin periodinane, and that looks like a better approach. The mechanism for this reaction, you can find it in page 551 in McMurray. The other thing that I would like to tell you is that the oxidation of a secondary alcohol, like testosterone, you can use either one of the oxidizing reagents. If you want, you can use the weak one. You can use the weak oxidizing reagent, and you will get the ketone. Or you can use the stronger oxidizing reagent, like a sodium dichromate, and you will also get the same product. Okay, the only thing left to discuss in the next mini video is going to be the approach of protection and deprotection.